Okay, so do you have any question before we start?
Question.
No? Okay, let's start the session. Okay, so this is one of the method under machine learning. This is considered as one of the most common method used for image classification, but it also can be used for regression analysis. So today we will look into how do we use neural network for regression and also for classification. So we will look into what are the processes involved behind neural network, the basic concept, and also do we apply neural network. Okay. So the discipline of artificial neural network arose from the thought of trying to imitate the functioning of the same human brain. Basically, they try to mimic human intelligence. But AI cannot imitate full 100% human intelligence. Computers can only be programmed to do some aspect of the human brain. For example, vision technology. We capture images and then we try to do um, image recognition, image classification, image identification. And also we look at the natural language processing that is part of our speech, part of the brain processes. How do we understand the text? How do we extract meaning from a paragraph or sentence? Or how do we perform topic modeling and so on? Okay. So if you look at the diagram here, we have multiple input, and inside the hidden nodes that are they draw a brain that process all the input that we get, and then we perform some action depending on what we intend to do or based on what input we get. Okay. But when we look into the more complex structure of the neural network, we say we have a deep learning framework in which we have a complex set of neural network with more layers of processing. So not only one layer, but we have more than one layer. So basically, these are the main framework for the image recognition, image classification, and also handwriting identification. So they are more powerful compared to the other method. So if you are dealing with images or handwriting identification, so deep learning is the best approach. Of course, the only disadvantages of neural network is that you need to provide a lot of example, a lot of samples for them to learn, and also they have so many parameters that you need to tune in order to maximize the performance of your deep learning. Okay, so the inspiration for neural network come from our brain. Especially when we're talking about the vision, because when we talk about the vision, how do our brain functioning in trying to perform classification or recognition or identification. So most important part is the neuron, because the neuron is the one who process all the information that we get from our input. So if we try to do a comparison between our brain and also the neural network topology. If we look at the diagram here, so the dendrites are the element that will receive the input. So if we compare to the neural network, we will have all the input that we have. So the yellow one is the input. So the input that we have in this neural network will consist of three input, x0, x1, and x2. And the processing is done by the neuron, which work on electrical signal passing. So the impulse will be carried out and will be released to the next one using this axon terminal. So this is your output. So if we look at the topology of the neural network, we have one output here. But before we can release the signal here, there is some activation function here. So the activation function will trigger the fire that will produce the output to right. So similar to here, so we also have flip some processes here. Okay, so this is your output, this is your input, and we also have the we call the nucleus, a cluster of neurons in the central nervous system. So this is your nucleus. So this the activation function is located here. So depending on the input that you get from all your input here, the dendrites, it will fire or trigger the electric pulse to the output. Okay, but the activation function here, if we talk about that one in neural network, we have a few formula that we can describe. And in ANN, we define the neuron as the CPU because they processes all the input, and then they will form a mathematical operation to generate one output. So your output is here. So depending on the activation function that we use, they will trigger or fire the output. And the output of a neuron is a function of weighted sum. So meaning that given input that we have, each input will have their own weightage. So when we try to train the neural network, basically we are trying to adjust the weightage in such a way that input given will match the output given in the training sample that we have. We also have this bias. We will talk about that one later on. So basically we have the input, hidden, and then the output. Okay? So for each of the input that we have, there will be a weightage. Okay, during the training, the weightage will be fine-tuned. Okay, and also the activation function. This is depends on which function we use, and the bias is used to adjust the weightage that we have. This bias will give you a more flexible condition in which you can make the output of your neural network to be matched with the actual one. Okay. So for example, output for your activation function will be the Y, and your input will be X1, X2, and X3. Each input will have their own weightage. So during the training session, the weight will be estimated so that given the input here, it will be matched to the given output that you have. So they learn your input, then they also learn the weightage so that it will map to the actual output that we have. And we have this bias because the activation function here will produce the output here, or will trigger the output here once they reach a certain value. Okay, we will discuss one later on. We also have this bias. Okay, so the neural network bias can be defined as a constant which is added to the product features and weight. So it is used to offset the result. Offset the result means change the output so that it will match with whatever desired output that we get. So it helps the model to shift the activation function towards the positive or negative side. This to adjust them. To adjust so that most of the positive and negative output will be matched with the actual output. Okay? So the one that will be tuned here or will be estimated here will be your weightage and also the bias. Given all the input you have and also the output. So there are some parameters that you need to know about the neural network. Epoch referring to one iteration, so meaning that it will go to one pass here, one iteration or pass through the process of providing the network with input and updating the network weight. Okay. But if you have a back propagation neural network in which it passed through the error here, so that means one epoch going one and going back here. So what happened during the training? Actually, in the training session, we are trying to estimate this voltage for each of the input so that given the input that we have, it will match the given output that we have. So there are several activation functions that we have. The first one is what we call linear function. So a linear function will give you the same value as the x. Okay, so this is the linear function. So if your input is 1, then the y will be 1 also. We also have this what we call unit step. Okay, for the unit step activation function, your output will only be 1 if you have x greater or equal to 0. Meaning that if the summation of your x, okay, the summation of your x is greater than or equal to 0, then y will be 1. We also have this what we call sigmoid. Okay, if you recall this one, this is similar to the logistic regression formula that we use for the formula. So the range is from 0 to 1. Okay. So it is slow convergence in such a way that if you look at the range of x here, range of x is too big. So big changes in x will only change your value of y very small. So that's why they call it slow in convergence. Okay. It causes gradient to vanish, meaning that any changes of x will not change a lot in the y because of you have wide range of x here. And this is very steep. Okay, so similar to if you have graph something like this, so any changes of x here will only change let me refresh that one. So if we have graph like that, a small change of this, no, very steep, okay, a steeper like that. Just want to compare. So if you have it's like this, changes of this, okay, this one will have slow convergence, means for you to go from to one will be much slower. Okay, so this is much slower. This is high. So we'll discuss more about the gradients on the next slide. Okay, we also have this hyperbolic tangent. The range is from -1 to 1. So meaning that if your value is x is positive, 0 and positive, it will be positive here. But if your value of x is negative, value for your y will be negative here. The maximum is 1, minimum is -1. So the gradient is stronger for this hyperbolic tangent than the sigmoid because we have stronger value here compared to the sigmoid, which is only here. Stronger gradient is stronger means whatever changes in x, it only will change your y a bit only. So mean that for the hyperbolic tangent, bigger the value you change in x, it will only produce a little change in your y only, because they have deeper slope. Okay, the best activation function that has been demonstrated in research is the rectified linear unit. This is the ReLU. Okay, the range is from 0 to infinity. Okay, this is simple and faster and does not have the vanishing gradient problem, because whatever change you have in here, you will have equal changes in y compared to the hyperbolic tangent and also the sigmoid, which is steeper. Okay, so we'll come to the gradient vanishing later on. Okay, we have this what we call the perceptron. Perceptron is a single neuron that classifies a set of input into one of the two categories, usually 1 to 1 or -1. So this perceptron usually use a step function, so which return 1 if the weighted sum of the input exceed a threshold and 0 otherwise. So if we look at the unit step function, so it will only produce 1 if your value is 0. Okay. If the input is less than 0, it will be negative. 0. Okay. So this is 0. So that is the basic architecture of perceptron. In the next lecture, we will study more on the perceptron. You have multiple layer, so they call it multiple layer perceptron. So there are two types of artificial neural network. If you only go one way, going forward, I call it feed forward neural network. If you feed the output back to the neuron itself, they call it back propagation, because you send back the message what was the error, and then they have the chance to readjust the weight. So for the forward propagation, meaning that you only go one direction. You have the input, this is your input, and then you have the hidden layer, and then you have the output, meaning that you only go one way, forward propagation. But if you feed back this one back into here, so they call it propagation of error, or they call it back propagation neural network. So this is what I mentioned just now. So feed forward means you go forward only, and this is sometimes we call it the back propagation. You send the feedback to the internal neuron so that they can adjust the weight that they have before. So the back propagation normally perform better compared to the feed forward neural network. Okay. And we also have this recurrent neural network. They are normally used for time series. So what happens is that they propagate the data forward and also backward. So this is forward and also backward. So this is a recurrent neural network. So if you only go for one direction, this is what we call forward neural network. Okay, so now we look into the gradient descent just now. How steeply the error will be reduced or increased for a change in the weight. Okay? So for example, this is your neural network, this is your input, and this is your output. And your output will be compared with the target that we have before, okay? And compare. So any error will be used to adjust the weight that you have. Okay? So number, okay, if we go from here, let me use different color. If we go from here, this is one epoch for the feed forward. Since we feed back the error back here, so our one epoch will be 1 and go back here. Okay, so if we repeat this one many times, several number of epochs, so we could adjust the weight so that we could minimize the differences between the output and also the target here. And the learning rate refer to how fast they can adjust the output so that it will match to the target. Okay, so if you look at the graph here, okay, this is the number of time we teaching them, allow them to change the weight. So if you're going to the right, you have more number of epochs or more number of tuning. Okay, if you look at the red one, okay, the more we train them, the more we reduce the loss or the error. So the red one is considered as good learning rate because the more number we train them, the more number we change or tune the weightage, we will lower the loss, will lower the error. So the red one is good learning rate. But if you look at the yellow one, so this is very high learning rate because you go down fast, but you also go up fast. Okay, so that means the changes that you make very big. So you go down, reduce, but later on you are not able to maintain lower loss. So you go up, meaning that as you go by here, you already lost the optimum value that you get here. Okay, so that's what we call very high learning rate. we also have the blue one. Blue one is low learning rate compared to the red one because you 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 have lower the loss, but not good as the red one. But still, you're able to lower the error that you have by giving you more number of epochs. The learning rate is you learn less. And if we look at the green, okay, high learning rate. Okay, high learning rate means you reduce the loss very fast, but suddenly you stop optimizing the process of lowering the cost. So what we want to have is this one. We want to have a good learning rate in which every time you adjust the weight, it will reduce the loss steadily and keep going down. Okay? So when we talk about the gradient descent is that talk about this one. Okay? So this is the gradient. Gradient is the slope. Okay? So what we want to do is we want to have a global cost minimum here. So we want to adjust the weight so that it will lower the cost here. But what happens if we make a bigger step, you will have go up here. So this is what happened in the yellow one here. If you make a small step here, then you will gradually lower down the cost here. Okay. So the objective of deriving gradient descent at each step is to find the global cost minimum, where the error is the lowest. We have to aim at here. So that's why when you put the learning rate is too high or the changes of the weight is too big, so you will pass through the global cost minimum, which is the minimum, and you go up to the next one, which is here. So that is what we call the gradient descent, which is an iterative approach for error correction in any learning model. How much change that you need to do in order to make smaller costs or to make a minimum cost. Big make you pass through, but too small you will have a slow learning rate. So in the neural network we have this parameter called learning rate. So that one also you need to optimize because different domain will have a different optimized value. So I mentioned just now, deep learning can mostly effective use in image recognition, computer vision, handwriting detection, text classification. Text classification because they can use the the RNN, okay, and also we have multi-class classification and so on. Also can be used for regression problem. So in this session we will look into this regression problem and also classification. The advantage of this neural network is that it can be both used for regression, also classification. Neural network are good to model with nonlinear. Nonlinear data means that you cannot separate the classes using linear line. So nonlinear means you have to draw nonlinear line to separate them. And they are very fast once you train them. And neural network can be trained with any number of input and layer. So this is another flexibility. And they are best with more data, but this is also the disadvantage of neural network. If you have less data, you will have lower accuracy. The one thing that we do not like about neural network is that there is no explanation why that particular item belongs to certain classes. So we cannot tell compared to decision tree that tell you why this new item belong to class A or class B. Okay. And nowadays for the image classification, you need GPU in order to process them. Okay. And like I mentioned just now, neural network depends on a lot of training data. Okay. Okay. Any question? They also said neural network are best implemented when there is good training data. So if you have plenty of samples, plenty of data, can use neural network. But if you have just a small sample of data, so your model could be overfitting or underfitting. Okay? And it says that more the hidden layer in the multi-layer perceptron, the better accuracy. You could investigate this one, and they say it is best to have 5 nodes only in the hidden layer. And they also say the ReLU best technique for activation function. So you can double check with this in most of the previously published paper. Most of them use the ReLU. Okay. Okay. So any question? Any question from you? No?
No, I
Okay, let's continue with the sample of how do we use neural network. Okay, for example, like this, given the input that we have here, this is your output. So based on the input, we can think about how do we get the output, right? So basically, we get the input and take the square of that, and we get the output. Okay. So the neural network doesn't know anything about this. So they only know given the input, and they should produce the same or almost similar to the output. So how do we teach them? Okay. So first of all, you need to install the package neural net. Okay. And by the way, in the RStudio, we have so many packages that consist of this neural network. So one of them is the neural net. So we're reading the input CSV from this file, and this is our input, and this is our output, and this is the row name. Okay, so how do we call the neural network? Okay, so if you look at the neural network here, this is where we call the function, and the formula that we have will be, because this is your dependent variable, this is your dependent variable. So we are trying to focus or try to learn this function or this formula. So the data that we get will be my data, and we have an hidden neuron. So a single layer with 10 neurons. And this is the threshold of your activation function. So when we plot them, so we can plot this one. So if you look at this one, this is the error that we have. No, this is the weightage that they will try to estimate. And this is the bias that we have. So both will be estimated by the neural network. Okay. So what we want to know is how similar the output that we can get when the same input that we have. So when we compare the output of the neural network and also the the actual output. So this is your actual output. And this is your predicted output from the neural net. So basically, we are looking at the yes, over here we are looking at the model that produced here. So this is the module produced. So we will get the result by focusing on the dot result. The dollar sign is focusing on that particular column only. Okay. So this is the result that we get. So in order to measure how much similar they are, so we could use the mean square error. So we could compute the value. So this is for the regression. Okay, now we look into another example here. Okay, so in this example, we will build a new version of the vehicles according to certain characteristic. So the what fuel consumption. So we want to estimate this one, the miles per gallon. So this is your dependent variable. The rest will be your independent variables. Yes, any question? No? Okay. So in this scenario, we have miles per gallon that we want to predict, given the cylinder, displacement, horsepower, the weight, acceleration, the origin. So this is the data that we have. Okay. And if we plot the miles per gallon, no, the weight against the miles per gallon, so we have the or we can have like this line we can draw. Okay. So if you want to look at the relationship between the mass per gallon and also the cylinder displacement, horsepower, and acceleration, we could use the plotting command. So you can see the horsepower has linear relation, or the displacement or the acceleration. Okay. And if we look at the data and also the standard deviation, okay, this one, if you look at the displacement and also the horsepower and also the weight and also the acceleration and also the cylinder, all of them have different range, minimum and maximum. But we do not want to have one column or one feature to have no influence on the output of your model. So what we do, we normalize them. So we normalize them using this formula, which is the mean and also the standard deviation. So what happened now? The differences between the cylinder and also the displacement will no longer be more. Like if you look at the cylinder here, this is 888, and then the displacement is hundreds. So when you normalize them, you will have almost similar values, but according to its own mean and range, mean and max. So don't forget to normalize your data. Okay, so meaning that we will perform the normalization from 1 to 6. So 1, 2, 3, 4, 5, 6. So we don't use the year, origin, and name. So we only take the 6. So your dependent variable will be miles per gallon, and your independent variable will be cylinder displacement, horsepower, weight, and acceleration. Okay. So once you normalize them, then we could divide them into training and testing. So in this example, we are using 70% of them as training. So we could use this sampling method in which we take the 70% of them and we put in the index here. So all the index will be extracted from the scale data that we have. So this one will have 70% of the data. This one will be the remaining. And in the next statement, we just get the list of names for the data scale we have here because we want to form the formula here. The formula here will be mass per gallon and tilde and all this value that we have. Or you could write yourself manually using this. So we will model the miles per gallon using the independent variable cylinder, displacement, horsepower, weight, and acceleration. So how do we call them? So we call the neural net. Then we have the F here. The formula that we form is here. And then we use the training data set and we use hidden tree only. So this is your tree hidden neuron. Then your linear output with some number here. So when you plot, you will have this one. So once you train them, okay, the net that we have is the model that we have is net here. So we will use the model net here to do the prediction. So we will use this command compute, and this is the model that we have. This is the test data that we have, and the result will be stored here. Okay. So what we want to do is we want to measure the differences between the actual miles per gallon and also the predicted value. So the formula here just saying that, okay, I will take the differences between the actual and also the predicted value, and then I will take the square, and I will sum all of them. Will divide them into number of rows, then the sum of all of them. So the mean square error is this one. So our objective is to get lower mean square error. So if we perform the same function for the linear regression, and you have studied this one in the previous lecture. So basically we use the linear model, okay, and measure the mean square error that we have. So we have this value. So if you compare with the neural network produce less value for the mean square error, means less error. And if we plot them, this is what we get. So the slope is almost the same. Okay, but this is the real versus predicted value for neural network. But this is for linear regression. Or any question? Okay, that is the sample of application for regression. Okay, now we take a look at how do we use the neural network to perform classification. So in this example, we have the breast cancer classification. Okay, so what we have here is we have the class here. This is your dependent variable, and the rest will be your dependent variable. So we don't need the ID because the ID has nothing to do with the class here. So what happened? We get the data from the breast cancer from the machine learning bench, and this is what we get. So we only consider all this, the size, nuclear chromatin, clearly mitosis. So we will not include this one in our modeling, and this is our dependent variable. Okay. Okay. So this is just to look into whether we have unapplicable or missing value. So we use here, we say that, okay, we will list all, we will apply this function if that particular row has an applicable value. So we will list all of them. So what we can find is that we have, which one is NA? Others, yeah. So we have all this value, others, which is NA. Okay, which cannot be included in the modeling. So we also look at the clean data. So here we are looking at all the breast cancer here. We will omit all the NA. Okay, and this is the summary of what we have. Basically, before that we have let me check. Oh, here we have this value NA here. Where else? Okay, so when we perform this, we omit all the NA from the breast cancer and we store them in the data clean. And now we don't have any of the NA that we have. So once we clean, so we can perform the box plot just to look at the average and also the first and third quartile. So if you look at here, we have different median. So we need to perform some scaling, and this is just to look at the distribution of the data for each of the column that we have. And this is just to look at the structure of our table. And by the way, we only extract two because the first one we don't need, and then the last one is the class label. So we will extract the second up to 10 only. So this is our input. And then also we look at, because some of them is factor. So these are not factor actually, they are supposed to be integer. Okay, because this like the size, thickness, so all of them are of type factor. So we need to change them into continuous value. So how do we change them? So basically we are using the function as numeric. Okay, so we change all the x as character and also as a numeric. And then we will apply this function to all the input that we have. and put in the input again. So now we have all numbers here. Once we perform that, then we have all the right value here. And since they have different range of minimum and maximum, so we will normalize them. So we could use the standard deviation mean, or we could use the min max method. Okay, so the min max method here will be used to scale them. So this is the function scale. We will perform the normalization the input, and then we using the min data and also the max data for the formula that we have here. So once we scale them, then we have a smaller number for each column that we have compared to this. This one we have 1, 5, 1, 1, and so on. And then this one is in decimal point. So the reason why we want to normalize them is that so that there is no individual column that have bigger influence or bigger bias on the modeling session. If you look at the class of your data clean, so we will extract that particular one and then put in the Kangsa here. And this is what you get. And the reason why we want to have two output, because later on we want to know if this is one for the cancer benign or this is one for the cancer malignant. So this one will transform them into matrix. So the cancer that we are from here will transform into this matrix here. So each column representing the class of output with each probability. So we will use that matrix compare with the output of the neural network that we have. Okay. So this is the final data that we have. So basically we will combine the column of the input scale. This is the input that we have normalized, and also the two column that we have for the cancer. So they are 1, 0, 1, 0. So depending on the type that we have here. Okay, so this is your final data that we have. Okay, and then we also training them. So this is your original data set. We will divide them into 70% and 30%. So this is how you use the sampling 70% of them, and the index here will be used to the ID number. So for the 70% will be stored in the training, and the 30% will be stored in the testing here. This is just to get the formula. So your formula is cancer benign plus cancer malignant tilde. So meaning that you have two output here, and you have many input. You have main input, two input. So this is how your neural network looks like. So we have 9 input and we have 2 output. So depending on the value of your neural network, you can compare. Okay. So here we have 5 hidden layer, 5 neuron. But if you want to have more hidden layer here, we just say how many of them. So we have example here. Let me show you later on. I will show you later on how do we add more layer here. So this is the topology that we have, and this is output that we get. So this is the model that we get from the training here. And we pass the data that we have, and then this is the result that we get. Okay, so the result that we get here is this one. So if you want to compare that one with the actual one, so basically we are looking at the differences between the data clean. We are looking at the table that will compare the original one. This is the actual one. And this is the prediction that we have. So the table will looks like this, and this is the error that we have. So we have 9 over the total of this. The total of this will be how many? 76, 52, 205. This is your error. Okay? So this is how you construct the confusion matrix. And if you want to put them in a table or a cross table, then this is how you pull them. So we are actually plotting the actual data that we have from the data clean versus the what prediction that we have. I think that's all. Okay, so from this example, we know that we can perform regression and also classification or categorical value. So we can both do the regression and also classification. One thing that is the most important part is the weight, bias, and activation function. So you have to know this. And also some of the parameter like the learning rate, the percentage of dropout, the number of epoch, all those must be tuned. In this example, we did not tune them. We just use the default value that we have. And we also know that there is input and also hidden layer and output layer. So this corresponding to how do we map to the data that we have. Okay. So any question? Any question? What you can do is that you can go through the exercise, go through the step-by-step instruction here. So you will know better on how to use them. Okay. You will have practical assignment on this, so don't worry. So you have to go through this exercise on your own also. Okay, so any question? No, huh? Okay, let me stop recording.